Hello, testing, testing.
Anybody else there?
No, it's just you and me at the moment.
Oh,
I'm expecting David because he sent emails. I'm possibly, I'm hopefully Justin and Michael.
I can't hear you very well.
Can you hear me now?
That's better, yeah.
Just put this a bit closer. Seems like David has found someone who knows about Beaker, whatever his name is.
Ledbetter.
Yeah.
He's the one that did remote viewing on the subatomic particle. Did Jan say he could make it?
I didn't get a reply from him, so I don't know if I'm assuming he saw the email earlier on.
I'll see if I can send him a message. Okay.
David. Hi, David.
Hello.
Hello, hi, David.
Hi. I took the freedom here to invite Matthias because he has done a lot of that motion that we spoke about last time. So maybe he can describe his conclusions there. Okay. He has been studying this in different kind of applications and has made some conclusions.
You said that you were inviting somebody to the meeting?
Yeah. Someone I have known for 20 years.
Ah.
Is it okay,
so
or should we
be
take
coming
he's prepared to join if you think it fits. Otherwise, maybe we can take it some other time.
Well, I had responded to your email. I said it was okay if he was interested in subquantum kinetics.
Yeah.
I mean, is he interested to be part of developing subquantum kinetics?
Well, there seems to be some some overlap. I met him this week, and we tried to look on this kind of motion. We were looking at the computer animation of that lead beater type of motion, and we came a bit close, but we need to do more to get anything.
Well, that's I mean, we don't know that that's the way it actually is. It's just a guess, you know.
No.
That's what they saw, but how do we know how good they were to actually see at that detail? I mean, maybe that was their idea of what they felt. You know? It's not like they took a picture of it.
Okay, so it's just a suggestion of how it might be then.
Yeah.
Yeah. Yeah, it would be good if someone could get some studies about this motion, because I just assume that some mathematician has studied it. Okay, here is Matthias, or I don't know how you pronounce your name in English, actually. Okay.
I can't hear him.
We can't hear you.
Speak louder. Or turn up the microphone on his computer.
Yes. The big background here is that we are looking for a certain type of motion that could be like a quantum for vorticity or spin. And then the Leadbeater structure was mentioned as a possible solution. And since I know that you have studied these kind of flows or motions in other environments, maybe you can give some orientation about what you have found. That was my idea. Matthias, can you hear me?
Yes, I can, finally.
Yes, so maybe you can mention some characteristics about these motions then.
Well, I studied Victor Schaberger in the 70s. That's what got me interested in vortical motion in general. And many years later, I joined the team of John Searle, if you guys know who that man is.
Yeah.
Yes.
And I stayed in that team between late 1996 to 2003, when there was a row and there were allegations thrown at the team of a burglary by Mr. Searle. And they were unfounded because John Searle had been basically begging a backer to fill his home with fancy televisions and computers and what have you. Anyway, when I discontinued my work with John Searle, I found the work of an experimenter, an American experimenter called Alfred Wakeman. I read some facsimile articles in Electric Spaceship Journal by this. I forgot his name. He passed. Anyway, this fellow, Alfred Wakeman, have been doing experiments in water and ink and vortical motion. And what he discovered was that you could produce a dual vortex motion in a spherical container. I think it was spherical, I'm not really sure, because it was never told what type of container he was using for the water experiments. But he was, I think he had a sort of impeller in the center, and when that impeller was rotated, and he created two vortices, one below and one above the imagined equator of the whole system.
Why are you telling us this?
Because I want to relate this to my later discoveries, which has to do with electrical vortices, or with electrons or charged particles in general.
Here we're concerned with using model G to create a vortex somehow.
Yeah, and
we're not simulating, we're not looking at an experiment and simulating the vortical motion. The vortical motion has to come out of the equations on its own.
Okay, so you're going the math route.
Yeah, the important thing is that we can have a self-sustain, like a superfluid or like a soliton structure of this kind of motion. So maybe you can just mention physically.
I actually wanted to hear a little more about his experiments.
Yep.
Maybe you can give a little higher level value overview instead of going into so much detail, because not everybody is as interested. But so could you perhaps do it a little higher level?
Yeah. Okay. But so just to finish this discussion of vortices in water by Alfred Wakeman. This motion, he created co-rotating vortices, because it was an impeller in the center, and that caused the water to move in this dual vortex system. And there was a secondary type of vortex created. That was the smoke ring type vortices on each side of the equator. When I mean equator, I mean the sort of imagined equator that you get when you have a.
So were these like two vortices that were sort of running? You know, Paul, like there were, you know, with the atoms, you've got some vortices moving together, and they're, you know, in this type of pattern, so that when this one moves this way, this one also moves this way. You know, they're sort of counter to each other.
In this water experiment, they were not counter.
So what was it? Two vortices?
They were co-rotating, but I'm getting now. Okay. I have to change. I have to go to somewhere else. Okay.
But there was like a mirror plane, wasn't it? So you got like a mirror image of the.
Like this way, that they were running this way, or were they running this way?
Can you take? I have to relocate here in my flat.
Were they sort of going together, but they would crash that way if they were going counter to each other, going this way. And that's what we're seeing.
The motion made now is the smoke ring. Yeah, actually, it's very easy just to Google Alfred Whitman and yeah, but what I'm getting at now is that after thinking a lot about the Searle machine and also reading some other interesting information, I came to the conclusion that you can create similar things with rotating magnetic fields and static magnetic fields. But in that case, those two vortices are actually counter-rotating.
Yeah, what I think could be applicable here is how you can describe that you have a stationary solution of this kind.
I can't hear. It's chopping up. It's chopping up.
Chopping up.
You want me to put a share screen of the vortical motion that we're interested in? Let me just go to see.
I can't really hear. They're very difficult to hear now.
Here we go. Let me just get it here. So,
could you mention something about the physical conditions to maintain this structure?
Can you see that?
Yeah.
Yeah, that's what we wanted to.
Yeah.
Yeah, and Matthias, if you have your pictures, maybe you can put them on.
I'm not sure how to do that.
You just
to show what kind of solutions you have found that apparently are stable. You just press, you move the mouse and then you get share screen on the bottom.
I have no idea how to do it.
Okay, so let me just I'll stop my share and then you can do your share.
So move your cursor down to the bottom of the screen.
Now you can do it because I've
then around the middle of the bottom,
and the green
you should be able to see a little green cursor with says share.
I got it.
And then go to the web page that
I got it.
You want to show.
I got it. Hold on.
So what's your background? Is it we're hearing that you worked on all these experiments, but what was your role? I heard some mention of mathematics.
I did. It's all chopped up. I can't hear you.
Okay, can you hear me now a little better?
It's chopped up. It's something on the way.
I think we're going to have to move on with a meeting.
Sure.
Okay.
Okay. Sure. I'll quit.
Hey, if you wanted to send some, are you a member of the Facebook group? You could drop some of your information and some of the links in there.
Yeah, I will. I'll try to do it. I'll write up.
Great.
Yeah.
That'll give us some familiarity with what you're working on.
Yeah. Maybe there are too many participants or something that cause all these chops.
Yeah, your reception's pretty bad. It's difficult to communicate with that.
Yeah, I can maybe hear 50% of what you're saying.
Okay.
Okay, we can move on, and then we can improve this presentation maybe to make it more applicable to Model G here. Yes.
Yep.
Okay. Sounds great. Okay, I look forward to it.
Sure. Yep. Yep. Okay.
Okay, so since the last meeting, has anybody done anything new?
I've been working on a couple little experiments. I mentioned the freezer experiment before, so I've been getting some of the equipment ready for that. That's the primary stuff that I've made progress on. I've also started looking at some of that the GitHub website that has all of
Stepper code.
Matt Pulver's stuff. So, what probably I've been thinking of what is the best place to put it. I think that, and how many of you are familiar with AWS? It's Amazon Web Storage. So you can put up one free server, and at least from a configuration build perspective, that might be a good place to, since we're sharing stuff, that's probably the best place to create a build off of Matt's stuff, try and work off of, what he's got. That way would be available to everybody. We could make one build and then it could be copied by other people and everybody could have their own little server. And then if they want to run something, they can just change the size. There's some configuration issues in regards to that. So that, it can be easily copied from one person's to another person's. So I'll look into how best to do that so that, we can have one single build and everybody can build their own server and then they can size it depending upon the tests that they want to run and the amount of money that they're willing to spend. So I do this making a living. So there are ways to create scripts and Terraform, that type of thing, so that you can have a build and it's copied over to other people's location, and you just hit a button and bang, they've got a copy of the service. So people won't have to spend so much time configuring things. They can just run things, bang, one after another. So has anybody, I know I heard other people ran Matt Pulver's software. Who else ran it? But Brendan, did you run his software?
The open foam, you mean, and the
No, not the open foam one. The well, we could look at an open foam build also.
You mean the
so if we wanted to have working sessions, so that when we do a build, we capture it so that everybody else can have the same build in another location, so everybody doesn't have to go through the same stuff. So we can sort of leverage everybody else's work instead of redoing the build. Perhaps I can do a lesson on setting stuff up in AWS, and then perhaps a couple of us can get together, and then if somebody's done the open foam stuff, and other people can work on, okay, how do we capture that build easily up in a cloud-based server that can be resized so it can run heavier loads.
I found open foam a bit tricky. I wasn't able to install it on my Ubuntu system. I could have if I tried harder, I might have been able to. So then I went for CAE Linux, and I installed that on my system, and that includes open foam. It includes an open foam wizard, along with the Salone computer-aided design. So I managed. So I'm just going through tutorials at the moment on learning how to use open foam in CAE Linux. I'm not quite sure if it's the same as open foam on its own, so I'm just working that out.
I'm just curious if there are any AWS builds for it.
I think the big advantage of running in cloud is that you can allocate a lot of different cores simultaneously, so it will be much faster. I did some, I'm trying to locate here on YouTube. I made some simulations, but they were not relevant. But at least they Here I have 5 of them. Do you want to see them or not?
So there's some documentation on the web for AWS and OpenFOAM, but not for CA Linux. So just an FYI, there looks like people have some builds already set up. Okay, I'm sorry I interrupted, David. Go ahead.
Yeah, it's trivial. You just pull down the code and you use some common compiler, and then it's working. You also need a library called FFTW. And here you can see I made a run there. You can open YouTube and watch it. It's not very relevant. The parameter settings were like unphysical, but at least you get an understanding of what the outlook is of a finished simulation.
So and so this simulation was of OpenFOAM, or was it of Matt Pulver's stuff?
This is Matt Pulver default settings.
Right. Yeah. So my point was, perhaps we want to create some builds that we could share, so everybody can work on the same machine. So we can, as opposed to everybody going through and coming up with a Linux build. And so, what machine did you run it on when you ran Linux? When you ran your build?
Let me think here. I think I ran on the Windows with Cygwin. I also ran on the Macintosh once.
Okay.
But it's rather trivial on all platforms.
Okay, so it's just because I noticed I was looking over Matt Pulver's GitHub site, and I looked at the requirements. It was, C++ compiler, version 11, FFTW. There, I believe there was NuPlot and FFmpeg and Ruby.
Yeah.
Some of that stuff's standard, but other stuff doesn't come with every build. So.
Yeah, it's a lot of dependencies there. If we can get some initial settings being the initial conditions being configured, that's a critical thing. Otherwise, it's just like starting the simulation and have it running for maybe 10 hours. I don't remember. It was quite a long time.
All right, since obviously it takes some time to do all this stuff, I think I might try and create an AWS build that has all of this stuff, and then put it in a form so anybody else can bring up their own version of AWS build that's identical. So let me look at that, see if I can get a build.
Yeah, or you can just send me some relevant and meaningful initial conditions, and I can put up simulations again.
Right. So the basic thing is
set up these initial conditions for vortical motion or lead beater atoms, and we can see if we can make a stable solution there.
Okay, so there's a few different things that happen. One, we want these simulations to run fast. So if we put it up in, like, let's say, a cloud environment, we can get it to run real fast because we can put it on big machines. I don't know if there are any parallel operations that we can use, so there's a lot of alternatives there, but just starting, let's just look at some of the sizing of the servers before we get into some of the parallel capabilities, because there's a lot of different IT solutions for that. So let's try and get some of the software, both the OpenFOAM stuff. I saw the CA Linux stuff, but I didn't see so many people talking about creating AWS builds. So I think that there's more work to leverage around OpenFOAM than necessarily CA Linux.
So best to try OpenFOAM on its own.
I'm thinking simply because I was looking and I saw almost no references to the CA Linux, but I just did one quick look, but I saw quite a few references and some detailed references around OpenFOAM and AWS. It was going into good detail. So if we can get some builds there, then we've got a repeatable environment that everybody can use. It's up in the cloud, and nobody has to reconfigure. We can do it as a group, and then everybody can leverage it. And we can also change the sizing on it. And because I'm foreseeing that I have some software that allows you to automate, look at this simulation, look at that simulation, look at that simulation, look at that simulation, that allows you to iterate through different simulations intelligently. So I would want to add that to the build so that we could.
So did you set up OpenFOAM? Did you set up OpenFOAM and have it running?
I have not done the OpenFOAM yet. But if I were to do, because I was looking at this link for, creating an instance on AWS. I'll just add it to the chat here.
How much will it cost, do you think?
So everybody can get a free copy of one small server. So we can work the configuration there, but when you start running stuff, it'll run slower because it's small, but you can change the size, which costs money, but you can turn it off. So it's
what I'm saying, will we need funds for this?
Yes, we could. How much? We have to look and see how the simulations run. So we can look at see how long the simulation runs, and then it's a small amount of money to do those initial tests to see how long some of these things run. So if you put it up to a really big server, you run it for a day, you're spending $30-40 maybe. If you run it for a month, then it's going to cost 30 times that, $1,200, whatever. Which is money. But certainly the first runs, if you're going to try and run it for an hour or, however long, it's not going to cost that much. That's something that it's manageable.
So
but it'll give us an idea.
For now, we can make do, but later we'll need some funds, right?
Yeah, and in order to get a good idea of what the funds are, we should probably do some setup first. Unless we're paying people to do the setup, then you want funds, but I don't think we're in a position to do that.
Maybe we could get some results first and then interest an investor, well, not investor, but a donor to donate some funds to move the project further.
What we need to do is also to determine how much RAM is needed to determine the physical size setup.
Right, so when you're working with the cloud, everything's virtual, and you can change sizes. So we can get an idea of what the sizes are, but we may want to start doing some parallel processing. Depends upon how the computation's done. We're just getting stuff set up now at the very beginning, a configuration that we can share. That's going to be a bit of work in and of itself. Then moving to the next step of performance is figuring out what the sizing is and how things run. That's another step. Then, looking at parallel performance, looking at how do you run multiple simulations at once, and determine what the next iteration is going to be. That's another step. So there's a lot of different pieces.
Well, maybe we should write these down and then we can check them off as we progress.
Sure.
Is that a good idea?
Yes. Determine how big the model needs to be. That's if possible.
Yeah, and so there's different directions to go with just, let's say Pulver's work. It looks like he has a three-dimensional version in there. I looked at that.
Matt said that he wouldn't be able to attend the meetings because he's very busy these days. But I'm sure if you have a question, we can send him an email. He'll answer it.
Did he provide any other input besides that?
No, he just sent me an email while we were talking.
Okay.
And just one line, that he's very busy these days and won't be attending the meetings.
But have you imagined how to set up the initial conditions to enable this kind of vertical rotating motion to appear in the solution?
So first of all, from what I'm seeing, the information that's coming out. So when you're typically doing solutions of something, you're looking for a specific result. The information that I saw coming out of all of this data was the amount of exons or yons in a specific location. And that's not going to tell us diddly squat about vertical motion. We're going to have to pull different type of information out of it. Yeah. So it's going to be a completely different mathematical model, which might mean open foam, which we could pull it out easily. Yeah. I'm not sure how the equations, I didn't get in depth into how the equations are set up or what type of information we could potentially pull out of those equations.
There are a lot of different tools available, but we need to like have a model or a geometry or a flow description that we put in as an initial condition, and then we can see if it's being sustained or being disturbed or dissolving. So without having the initial flow pattern that Matthias has studied, we can just set them in initially and see if that
well, there is a flow that we would expect. It's the spin of particles. Okay, so that is.
Does David understand? David, do you understand why that vortex would develop? I mean, in the particle.
Does it have to develop, or could we put in a already designed flow type and just see if it remains stable?
All right, so the two forces that are working.
That's the thing. You can't just superimpose stuff onto the model. It has to come out of the equations.
Okay, so what the model has already are two things: reactions and diffusion. So when you have a reaction, it's going to be in that single space. You're going to have new particles forming, and then you're going to have diffusion, and diffusion is what's causing the motion. And that diffusion, you would expect just from the equations that the diffusion itself would be creating the vortical motion. Now, we talked about all different things. Well, if we don't see any motion from just the diffusion, any vortical motion just from the diffusion, there are other things we could add in. We could add in, some mass. There's inertia from the reaction. There's a lot of different things that we get in to try and capture that.
I'm not sure we can put in inertia if that is like a resulting consequence of the constituents.
Well, okay, so the reaction might have some inertia. So when you have a reaction, it might push off some of the resultant etherons in different directions, okay, which would then chain reactions, and that would give you the vortical motion. So that, here you've got a reaction, and the exons, yons go this way, the pions go another way.
I understand that you want to like having this flow to emerge from some more trivial conditions, but there is, if these conditions are hard to find, we can like put in the end type of flow and just find out if it's stable
Absolutely. Or not. There are many different ways of attacking the problem, and that's an extremely valid way of doing it. But the end result is we're trying to get a mesh of the reaction diffusion, or if it's not that behavior, some other behavior. But reaction diffusion is very enticing because it's very simple. It simplifies the model dramatically from a computational, from a physical perspective of how things behave.
I was just sharing the screen here. I'm going to share it. So this is Open Foam, and it's one of the tutorials, and it's showing. See these equations here and here. It's showing how Open Foam.
I don't have the screen. How do you get the screen?
Can everybody see it? Can you see
yes,
it?
I see it.
I can see behind all the people.
Click on the window. There's
which window? The window went away. I don't know why. For me,
you might. Okay, so click on the bottom bar and look at your applications that you have. And
that window has disappeared. All I have is this. Let me see. Here's a square. That's for you. Yeah, I don't know. Okay, all I have is the four windows.
I'll stop the share. Can you see yourself now?
Go ahead. That's okay. I'm not able to see your screen, just you guys.
Can you see it now? Oh.
No.
Anyway, what I was showing here is this is the user manual for Open Foam, and it's showing differential equations, and it shows how to input them in the code. It's just a tutorial. And then further down, it shows, well, first of all, it was to do with, let me just get back to the top. First of all, it's a breaking, it's a tutorial of a breaking dam. So it shows a water column in relation to a dam. And it shows you how to set up this is 2-dimensional. And then how it shows you how to set it up within OpenFOAM, which I don't think you can do with CAE Linux. I'm not sure you can do it with that. So at the bottom, it shows the part of the simulation here, and then further down, it shows the resultant of the simulation.
One thing here, if you use the original equations, you have so small differences that you need to do some operation, and that was something that Matt did. Otherwise, the deviation from the static is too small to actually be used on a traditional computer. Are you going to use Matt Palmer's method of some kind of reduction of parameters?
Well, that's going to be the easiest thing to do first. I mean, create a Linux build in AWS with Matt's stuff on it, and then the next thing would be, try and run it. And then the next thing, and then share it with the team. And then the next thing would be to add OpenFOAM and try and run some of the simulations. Now, one of the things about when you have these servers up in the cloud is the screens that you get are you don't really have access to the screens. You're really working with things from a text perspective. So we're gonna have to look at that and see how we can get the views out. Obviously, if we put it in a browser, then those things are, those types of servers are excellent. But if we're serving web pages, that type of thing. But if we're serving like user screens, then that environment's not necessarily the best environment. So
yeah, it would be easy to make a web interface just to set up the initial conditions and just to control the simulation, like starting it, seeing the status, or stopping it, and listing already finished simulations, and viewing the videos, result videos.
Right. So we may need to also have some versions in order to see things on our own screens, but they're obviously, I'm looking at all the documentation here, and they're obviously running simulations up in AWS using OpenFOAM in AWS, and in order, from a computational power perspective. So, that's what all these articles are about, how to do that.
Yeah.
So we'll just see what method they use to do, to look at the visualizations. And they may download the results and look at the visualizations on their laptops or what have you. We'll just follow along with what they have in these tutorials. But it's a very reasonable technique to use.
So in the beginning, are we going to be simulating without the Navy or Stokes, and just see if we can get vertical motion if we simulate in 3 dimensions? We had talked about that
might be okay. So first of all, we have to have some computational method for seeing motion. Right now, we're running the equations, but the results we're looking at are not showing us motion. So we have to pull motion out of that, because all we're seeing is, okay, what's the quantity at this point in space? What's the quantity at that point in space? Xons, Y-ons, and G-ons. What's the quantity here, quantity there? We're not seeing, okay, these exons moved from this location to another location, and then they moved to another location. We're not tracking that motion of individual pieces, so we're not tracking the group movements, because we're going to have to track individuals, then track groups, and that's going to tell us, the vertical motion. So we have to get the motion out of the running equations, and we may be able to do that with the existing equations we have, or with OpenFOAM. OpenFOAM, natively, they show that type of stuff. With this type of equation, it doesn't natively come, but we may be able to do something with equations to get it out. We'll look at the difficulty of the two.
And also, I think the first thing to do is to get OpenFOAM up and running, run some tutorials, and to just
Correct.
be able to get it running first, because I know
Absolutely.
I have some
And some of us have to get, Matt Polger's. I ran his stuff on the web. I don't know if I ever run it on a laptop myself. The Mathematica stuff I did run, and I ran the web stuff, but I don't think I got his C++ stuff running on any machine of mine.
That's the ETD stepper. That took about 2 days to run on my computer when I ran it.
Yeah, that's what it takes.
How big was your machine?
It's 500 gigabytes hard drive, and it's the RAM. I think
you need
8 gigabytes RAM. I think
you need more than you need like 10 or something, 12 to run the default 3-dimensional settings. You can make a smaller model, but then maybe you lose precision. So if you watch the video I sent you, that's run on 10 to 12 gigabytes of memory over 10 hours or something like that.
Hey, Matthias, glad to see you join us again.
Yeah, I was begged to.
Yeah, one idea I had here was to put in the motion in the model and just to see if it's stable, because we don't, as of the current, know how to put up the initial conditions for this kind of motion to appear. That would be even better if you just knew how to do that. But if you can provide the motion, then we can eventually put it in the model and just see if it can remain as a stable solution there.
Well, I think we need to see the motion coming out first. Putting motion in, the motion that we have going in right now is just diffusion. That's the only motion function within the set of equations.
So we cannot have, can we, is it possible to conclude that the traditional motion is impossible, that is like a particle can move?
We have, it's how the computational system's set up. We have to have some way of viewing the motion. We're not measuring that in the current output from Pulver's equations. What we're measuring in the output from Pulver's equations is just the quantity at every single point. We're not measuring, these exons move from this location to another location based upon diffusion. We're not measuring it, so we can't see anything if we're not measuring it. So we have to try and measure that.
Doesn't SQK include motion? Like the potential, like the concentration is like the potential. And
well, we got the diffusion. The equations include diffusion.
Yeah, so you need the diffusion to go in a circle instead of radially, which right now it's going radially. So
that would, that's assumed. And you're not so from any specific diffusion.
Yeah, that's
for any
water physics. We can see a lot of examples of that.
Yeah, diffusion doesn't operate radially. A chemical reaction might act radially, or it might act, in a linear motion. Exons go in this direction, ions go in that direction, etc., depending upon where things are coming in for the reaction. So you see all the different additional complexities we have to add from an equation.
Fluid dynamically, these kind of solutions has been studied beginning with Taylor. He got Coriolis forces that prevented diffusion in one direction. It went in a curve, so it was like limited to go in radial direction, and at the expense that you get a very high diffusion in the tangential direction. This is called Taylor diffusion, if I'm not remembering incorrectly. You can check it up, that you can actually get changes in diffusion characteristics based on rotating motion in the fluid.
I'm hoping this video meeting will go on longer than 45 minutes. Last week they gave us an extra time several times, so it may stop shortly. If it does, I'll set up a new one and send you all a email, and we can keep going.
But can we? How would we then? Can we then just?
I just set up a new meeting, and you just click on the link and join it.
So you just drop something in Facebook, and we would rejoin the video conference.
But it may just keep going. So it's 45 now. 45 minutes now.
I just want to say that you have the core of the particle, and then outside that you have the shell. So you're getting diffusion from the core to the shell. That's radial. That's the way it is now. To get the circular vortical, you need somehow, like in rotational waves, that circle becomes divided as like a bifurcation. So it's no longer, this central core is no longer unitary. It's divided in two, and the two end up chasing each other around like yin and yang, which would obviously create some vortical motion. They've shown, they've done some work in rotational waves, but I don't know how to create them with model.
Well, we could just rotate the inertial system then and see what that would cause on the solution. You get a different kind of diffusion change in that way. The diffusion is going on curved paths because of the rotation, which means that it won't go. It goes in small circles, so it cannot go arbitrarily long.
David, did you want to cover that next time? You know, you say go
Yes,
up.
I have all presentations on that.
And I can cover that next time, talking about some of the servers and loading the stuff up there.
I have been presenting that some years ago in a meeting in Sweden just to get people to understand this, because they don't. And they have shown this in practice, having a rotating water and dropping ink into it and seeing that it's not diffusing as if it does in solid still water because of the rotation of the water.
So okay, I understand it from a physical perspective,
yes.
But at the microscopic level, of
yes, it's the same
reactions. How is that being created? If they said they were doing some math simulations, how are they getting that to happen? Are they saying that when the reaction I'm assuming they're doing a reaction diffusion system, since that's what we've been talking about. How are they getting some type of beginning vortical motion at the microscopic level?
Yeah, that's too big for me to start to imagine how to make some small initial conditions that will develop into a bigger, stable, vortical
Well, did they actually get that out of some of the mathematical equations? Perhaps somebody can dig into that paper and see how that information was being.
Yes. What I can do as a first step is just to find these kind of motions, the motions that Matthias has been investigating from a more empirical perspective. If we can find some good descriptions of that, it would be a big help, I think.
Right. Because we can imagine a lot of different ways of putting it in from a computational perspective. I mean, we talked about some that, perhaps there's some mass associated with the different things that might cause stuff. The reaction might be pushing, certain, etherons in specific different directions which would then chain, and then you would, based upon how everything's chaining with each other, you would get the motion.
It might be possible to include Navier-Stokes into open foam, if it's not,
right.
or the rotary equation for rotary motion. You might just be able to, with the Model G, you might just be able to add on a part to the add on a term to the equation. Or open foam may already simulate Navier-Stokes because it's used in fluid dynamics and weather modeling and things like that.
One idea to create that initial rotary motion that David was talking about, you could have 4 advections imposed that are off-centered from the center of the particle. So it would create between the 4 of them sort of a rotation.
So that would be
Matt did that with the geons. He had a geon wind, and you saw the particle moving down the gradient. Well, it was a gradient, and it also created a flux in that direction. Well, we could do something like that, the way he had imposed that gradient.
I think that's great, because that's part of how all this works. But in order to get all of the particles themselves creating that vortical motion, from inside within the reaction, I think that's sort of like the end goal, because we want to be simulating these things outside of any specific wind. because in that
Yeah,
case,
well,
you get
Matt,
particles forming in one way depending upon the winds.
yeah, Matt had put in fluctuations to create the particle. It was like just a momentary potential, and then it would disappear, and then that would trigger it, so it would develop. And so I think we would be doing the same thing to try to trigger the vortical motion and hope that it continues.
Triggers are absolutely, something that you want just to get things started. So that's very understandable. That's very reasonable.
Okay, so do we need to continue the meeting or we got enough things to do till next week?
So the first thing for me is to get open foam installed and running, and run the tutorials and make sure that it can actually make it do something.
Okay, so when I get around to, I'm going to try and put Matt Pulver's code up on one of the AWS servers. When I get that done, I'm going to try and ping you. So whatever you're doing to get it to run in your environment, I'll ask you to try and work together to try and get it running in an AWS environment. So then we can just clone these servers. So everybody has it. Does that make sense?
Yeah,
Brendan?
I can. I have a continuously running server here on VirtualBox. So if I can make up the solution, it can easily be cloned.
Okay, I'm not familiar with the VirtualBox, but it might be a similar. I use DigitalOcean. I use AWS.
If you have a VirtualBox clone, you can just copy it and run it on almost any computer, modern Macintosh, Windows, or Linux.
Okay, as long as we have a clone of an environment to work with, that's fine too. The one advantage with whether it's DigitalOcean, AWS, Azure, whatever, is we can change the size of the darn thing. We don't have to go out and get physical pieces of equipment to run.
Yes.
And so that's why I'm sort of saying, hey, for our needs, in order to change sizes and also to let people, instead of having to copy stuff down, the environment's automatically available to everybody everywhere. I'm not trying to push for these companies. I'm not, a big fan, but these are good services that provide these capabilities.
Yeah, I have maybe 8 or 4 cores here, and you can easily buy 96 on the cloud. So it will be like more than 10 times fast. You will finish in less than 1 hour if you buy a service. For $4, you can make one run in 1 hour, apparently, if it scales linearly. And if you use the default settings for 3 dimensions.
Okay, so I'll ping both. Once I have an AWS build, at least with Matt Pelver's stuff, I'll ping both you and Brendan to see if you have a build that I can of open foam that I can pop up there. I didn't quite catch what you were saying, David. So if you were describing something different, please speak up.
Yeah, I can go into my old runs and see what the requirements were, so we can get some understanding of how long time it takes and how much RAM it consumes and so on. I'm just taking as far. This was several years ago. Was it 4 years ago? 5? So I can't really remember, but it's yeah. On Windows and Linux, it's rather trivial to set up.
It comes prepackaged on my distribution, at least, Debian.
What comes prepackaged in Debian? Ruby, I think.
OpenFoam.
OpenFoam comes on your version of Debian, comes with OpenFoam?
Yes, it does.
They also have
a fork called FreeFoam.
But how far have you gone on modeling on OpenFoam? Because there is a lot of things to consider.
Who were you addressing?
Anyone who has an answer to this question. Maybe Brandon, if you have been looking into OpenFOAM.
I was looking at it, but I was trying to install it on my Ubuntu system, but I decided to go for I couldn't do it at that time, and I decided to go for CAA Linux. And but it seems that OpenFOAM may work. You've got more control, and you can do more things if you run it on its own. So I'll go back to trying to install it. I just need to research it more to try and work out how to install it the best way. When I've got installing it, I'll run a tutorial just to make sure, just to familiarize myself with it and learn how to use it.
Yes, yeah.
I haven't seen any Debian builds with OpenFOAM on them, so it's counter to my experience and knowledge.
I came across a presentation which described how to set it up, so that may be more useful than what I had before. But it seems that it's got equations, it's got fluid dynamic equations. It can give us some ideas about mass and velocity, and we might be able to go into OpenFOAM, put our own equations and our own G model equations in there, and then select the motion and mass equations to go with it.
Perfect. Okay.
Process.
So that's perfect. You know, if we can get OpenFOAM right, because the outputs from something like OpenFOAM are where we're going to see motion. That's where we're going to see the vortical motion, meaning potentially vertical or whatever. That's where you can see motion of things. That's where you can see the waves and the fluids moving. That's
and then
what those patches are built
I was
for.
thinking that you've got the motion of the fluid, but each point in that space, you've got the concentration. You've got the X and Y and G concentrations. So that would be
concentrations, but you also have motion. So,
yeah,
and that's something we don't have in Matt Pulver's current work. So my opinion is the direction you're mentioning, Brendan, is the appropriate direction to go. I'd hate to try and build something into a set of equations, no matter what it is, such as Matt Pulver's, doesn't matter what, because that system is not built for getting fluid motion out. OpenFOAM is built for getting fluid motion out. So it's the natural direction to go. Working with Matt Pulver stuff is just to get some familiarity with some of this stuff. But my opinion is, you know, OpenFOAM is the direction to go. They also have some stuff for reaction diffusion. I know I saw things like Blender, and I know Blender's got some fluid stuff in it. And I think I even saw some
within that
reaction diffusion stuff in it.
So within that sort of like reaction within that fluid dynamic model, we'll have the etherons, and the concentrations of the etherons will be the density of the fluid. Sort of
right. So all the equations that you see in Matt Pulver's stuff and all the papers that Paul has written, those are the.
Hello.